think, Max? Should we get started? Okay, great. Hi, I'm Hans Johansson. I'm the guest lecturer for Phil today. We're going to cover multigrid, and he said that initially you had started off doing some structured grid work earlier, so I'm going to try to go back and refresh your memory on some of those things. My background, I actually was one of Phil's graduate students in mechanical engineering over there in Etcheverry Hall, and I spent about 20 years in commercial technology and financial services, and decided to come back to Lawrence Berkeley Labs to get back into scientific research and large-scale computing. So hopefully I'll teach you something about multigrid. I've heard that a number of you may have done some multigrid work already in 228. Okay, so I'd love to make this interactive, so feel free to ask any questions. Happy to whiteboard things or cover topics in depth if you're familiar with things already. Okay, great. All right, so let's see what we've got here. So I'm pretty sure Phil covered this already, but his dimensionless notation here, where you can express the Laplacian as a sum of each dimension's second-order derivative, and you're doing it on some domain that could be, nice and union of rectangles or squares. You can do it on more complex domains. You might want to grid this with an unstructured mesh, or some of the approaches that I use are actually to do things called cut cells, where you overlay this on a regular Cartesian mesh and then kind of fix up your discretizations around the boundaries. So Poisson equation, I know you've talked about that already a little bit. Heat equation, another flavor of this, where you can set the solution to 0 on the boundary and ask things like, how long does it take for the temperature field to decay or to reach some steady state as driven by this heat source term. You see that a lot with reactions, with kind of complex multiphysics chemistry. And so these are things that are good model equations to understand. The key thing about both of these equations is that unlike hyperbolic equations, these have infinite wave speed, right? So for example, for this time equation here, when you look at how quickly the solution evolves, suppose it was 1 in the middle as an initial value and 0 on the boundary, immediately the middle of the domain, after any infinitesimal time step, will feel the impact of the boundary conditions in how the solution evolves. So these things are considered to have infinite wave speed, and that creates problems for numerics, where you end up having to do implicit methods or solvers in the case of Poisson equation, where every part of the domain depends on every other part of the domain. And that's why we talk about these things in terms of implicit or other approaches. So for a rectangle, you did finite differences already, right? Or you've done it in past classes, I think. So we do a simple second-order accurate discretization of the Laplacian. Again, this kind of dimension-independent notation where this is the stencil you apply in each direction. So in 2 dimensions, this gets a -4 in the middle. In 3 dimensions, it gets a -6 in the middle. And these are all second-order accurate in whatever the grid spacing is h there. And we do it over some rectangular domain. And this is what would be called a nodal discretization. So here, the finite differences would be to calculate a Laplacian here, the difference of values between those 2 locations and the neighbors, and you get a value out of that. So that's how you end up with this -2d times the middle point plus the sum of everything around it. So because we're only defining these on the interior values, we need to specify a value on the boundary, and that would be, for example, a Dirichlet boundary condition where we're saying the solution has to be 0 there. And then we can calculate everything in the interior pretty much with the information we have, and we're able to actually kind of do this calculation. Now the problem is, this is a very small domain. You're not going to get very good resolution here. We want to do this on the order of 10,000, 100,000 in each direction here, so we can end up with a billion unknowns in a 3D problem very easily. And that's why we're looking at this for supercomputers. So if we want to solve this Poisson problem by solving that entire finite difference discretization and inverting it for a given right-hand side f, we have to figure out how to take this stencil, and I think you already studied the point relaxation schemes, right? Point Jacobi. Did you go past that into Gauss-Seidel or anything else? Okay, well I won't cover those, but if it's something you want to learn more about today, I can jump into it real quick. But by doing that, we basically take those values and we're able to invert the equation. So let's look at what that looks like. So for point Jacobi here, That's right, you studied it for unstructured grids. So this is a lot easier. You know exactly what the structure is, you know what the diagonal values are. They're not changing as a function of space because your triangles are different size or different orientation. So we end up with this very simple equation for relaxing the Laplacian and its right-hand side together. So this is effectively a residual times the relaxation parameter, which we're going to discuss soon. And then that is an update to our iteration for the next guess at L plus 1 for every point in space. So that relaxation parameter looks effectively like we're marching a time, pseudo-time from L to L plus 1 with some time step relative to that. So if you've studied time integration schemes, you know that for a big enough time step, it'll blow up. It's unstable, right? So we're going to talk a little bit about the Fourier analysis here to ask, what do we need to set lambda 2 to get the effects we want? We could set it to 0 and never make any progress. We could set it to something too big and it'll blow up in terms of your iteration. So somewhere in between is the magic number, and a lot of what we're going to talk about today is what those magic numbers are. So I know you've done some discrete Fourier analysis for coding up FFTs and that kind of stuff. So I'm going to talk about this entire multigrid lecture in the context of these Fourier modes. If you look at the Laplacian here and you discretize it with that second order accurate centered stencil, all the eigenmodes are effectively, for example, if this were Dirichlet boundary conditions in 1D, these are the eigenmodes. They're all the sinusoids as represented on that discrete mesh. So you can imagine, some of them are super oscillatory in this plus-minus mode. These are the super smooth ones, even at really coarse resolutions. This is only, 16 points. And every time we do one of these point relaxation sweeps with some kind of relaxation parameter, the solution gets a little closer to its final solution value. And if you look at this, you can see that the middle is not really affected as much as these corner points where your guess is already good and just kind of like slowly creeps towards it. So even for such an incredibly small problem, n is equal to 16 here, and this lowest wave number, which is about as smooth as you could get, you're going to spend order n squared operations just to get to this kind of finite error. If you actually want to get it to converge to something reasonable, you need order n cubed iterations. Now again, if n is on the order of 100,000 or 1,000,000, it's not going to work. So that's the whole point of these kinds of approaches that we're going to talk about today, is to get that scaling to work for larger problems and bring it down to something that can converge much faster at scale. So let's look at kind of what happens here. I seem to remember you did this kind of correction residual mode before, so I'll talk a little bit about it. But basically, with this substitution, this isn't a realistic substitution because we don't know what the exact answer is, right? But we're saying if we flip the equations around and assume we knew the exact answer, when delta goes to 0, then we know that this iteration is converging to the exact answer and we're done. Well, I'm sorry, exact discretely. It is our final answer. And so doing this kind of correction analysis, we can figure out, for example, that if our residual is going to get damped down quite a bit, we're going to be able to find some epsilon where we're able to say, we'll bound, given the right-hand side, we'll be able to bound our residual, and that will then tell us what a bound is potentially on the error. And so when we do these iterations in this correction mode, the residual actually disappears because when we're done, delta is 0. So this is the equation that we can analyze even though we don't know the final solution. But this tells us from a behavior standpoint how rapidly that error delta is going to 0. So that's why I flipped this around a little bit. Now we're looking for ways of, instead of increasing the solution, we're looking for ways of damping the error. So let's look specifically at this is, for example, a step size you could take for this relaxation parameter. And for that relaxation parameter, you're going to end up with something that kind of scales nicely. The h squared would cancel with the Laplacian here, right? You get that dimension independence where we cancel out the diagonal terms, just like you would with point Jacobi. And you end up with this update equation. And if you actually substitute in the stencil values and simplify this, you'll see that this looks basically like a weighted average. What it is, for example, these are off-diagonal elements in each dimension. So in 3 dimensions, we would have 6 of these. That would be 6. So basically, take everything off-diagonal, average it, and then average it evenly, 50%, with the diagonal value. And what would this do? Let's say, for example, we had a constant. Well, this would preserve a constant. This wouldn't change at all. So that's maybe not good, but a constant doesn't fit the boundary conditions. It'll iterate eventually because you'll have some change between values. Also think, what would happen if this were in a plus-minus checkerboard mode? Then a diagonal entry here could be a positive value, let's say, right? But all of these off-diagonal entries, your nearest neighbors, would be negative values. But since it's a simple weighted average of the two of them, immediately this correction goes to 0. So we have effectively killed that checkerboard mode. So that's what this choice of lambda did here. And somewhere in between all the other modes, from the smoothest thing you can do, that first wave number, all the way to the highest wave number plus minus, they're being damped to some extent. So that's the goal here, is to look at this stuff from those two extremes and ask, what do we want and how fast should this converge? So checkerboard mode went to 0 immediately. Smooth modes get damped very slightly or don't change at all. So weighted sum, positive weights sum to 1. Min-max values are always strictly decreasing. This is important. If you think about mathematically the maximum principle for either Poisson equation or heat equation, this effectively is the discrete equivalent of it. If you're stable and you do this iteration, you are bounded in terms of the strictly decreasing error. So what this is doing is that with those plus-minus modes, that damping was immediate to 0, right? So you're basically putting a bound based on the frequency of things. And all of this looks like effectively is a time step for the heat equation. Heat equation, because of the Fourier analysis and other arguments you can make, will take the highest frequency components and beat them down fastest. That's why an inverse heat equation is so ill-posed, right? The highest frequency components are gone from your initial condition, and you can't say what they should have been because they disappeared from your solution so quickly in the forward problem. So those kinds of questions, the higher wave numbers get damped very quickly, but the lower ones take longer and longer to decay. So let's look at that specifically again, but now we're going to start upping the resolution. And tell me if you can't really see that from there. I'm more than happy to, maybe I could zoom in or something. But this is, and I didn't even print every iteration here, but if you take 120 iterations, 128 on a 128 size problem, that's the end solution we're trying to get to. And so this is basically the difference between that line and the solution is the error that's remaining. So you can see that it's making incredibly slow progress about that. So we did 64 times the work in going from a 16, n equals 16 problem to an n equals 128 problem. 64 times the work, and our error is actually getting worse with resolution. So again, if you want something that's numerically converged, if you want an accurate answer, you have to start running a different problem in order to try to fix this. But let's look at some other wave numbers. So this would be k equals 2, for example. It's getting at least halfway there with the same number of iterations. K equals 4, we're getting very close, actually. Let's say 10%. And then finally, you know, if you look at some of the highest wave numbers that can be represented here, so this one is basically 8 points per wavelength, we're right at the exact solution, more or less. So basically, this shows you that the error that you're going to get here kills these high wave numbers first, but it's going to leave the smoothest error that you have. And somehow, as the problem gets bigger, you're going to get fewer and fewer small wave number modes and more long wave number modes. So we've got to figure out a way to address this. And so we're going to look at it from a discrete Fourier analysis perspective. So in particular, so I hope this looks familiar, because I went back and looked at, what, 3 weeks ago, FFT slides? Kind of, maybe, OK. Well, I'll go over it again in a little bit of detail. So you take wave numbers. Suppose I have k points, then I have k wave numbers. And you split them in a spectrum between negative, which are symmetric with respect to positives, because you've got a real problem, therefore you have that relationship between the coefficients. Okay, and expressing this as an inner product with this kind of a weighting here for your wave number modes, that would be your value at a point. And what you're doing is you're doing a Fourier transform. So these are the Fourier coefficients of, for example, the right-hand side here. And this z to the kj is e to the 2 pi I h to the kj. So each of these effectively represents a grid wave mode. Multiply it by k, the wave number, to get the oscillatory nature of it. And j effectively is a shift for the location of that Fourier mode in real space. So by doing this convolution with that kernel for discrete Fourier analysis, you can see everything from wave number 0 up to the maximum wave number, which is a plus-minus mode on this grid. Right? So all of that is basically It's a one-to-one, so you know that you've not missed anything with the transformation. The long wave numbers and the short wave numbers are all represented here. It's just a matter of incorporating boundary conditions and looking at the symmetries too. So one of the things that we also learned, I think, in the Fourier analysis was that with a finite difference shift operator, if you can just envision taking this, shifting it by 1 point, so making j to j plus 1, then you end up with this 2 pi I k h factor multiplying this term. So that's all this is. Effectively, it's saying anytime you do a finite difference shift, it's the same as multiplying it by that quantity for the wave number, which you can imagine, right? So if you shift a low wave number just a little bit by one cell, you're going to get just a small change. If you shift a high wave number, it could be flipped sign, right? So this helps you understand that that finite difference operator for the Laplacian there ends up having basically all of those modes from shifts and summations get wrapped up in this lambda, which is a wave number, modifying the Fourier coefficients for the thing you put in the first place. And that lambda looks just like your finite difference operator, but with each of the shifts turned into this complex multiply. The center scheme, identity for k is, for the shift of 0. And then a left shift would be the minus. And so basically this modifies our Fourier coefficients from what we put in, which was f, and what we get out, which is lambda times f. And so basically anytime you want to invert a fast Fourier transform, you just divide by this diagonal coefficient and you get back your exact solution, and that's nice and easy. Except doing fast Fourier transforms at scale, I think Phil talked about that a little bit, is a challenge, right? It's a lot of communication, they don't scale well. But at least you can actually kind of see what the effect would be, and sometimes even doing this locally can benefit you. So basically, to rehash, any finite difference operator that is linear, because Fourier transform is linear, we can represent in this way, and we can invert it to find out what its effect is on a given wave number, and then look collectively at the wave numbers for our operator and figure out what the effect is on it. So it's a really nice analysis tool when you're doing finite difference methods, finite volume methods, finite element methods, it doesn't matter. And it's basically a specific example of an eigenmode analysis for the operator and the discretization. Now, so here, this diagonalizes things, but in other cases, you don't have such a nice thing, and it's a discrete set. For example, a finite element mesh with the heat equation or Poisson equation has its own eigenvalues and eigenvectors. But this is basically a shortcut for us to do this in this specific scenario so we can do some analysis. OK, so let's see what happens to our point Jacobi correction equation. So here again, we're relaxing. Take the Fourier transform of everything. It's linear, so the only thing that pops out is this one factor here, lambda k, which is now a factor of the wave number. So this shows you immediately that our damping effect is wave number dependent. And because these are the same thing here, we just gather terms, and we end up with this damping factor omega of k for a given mode that takes the old Fourier numbers, I think my battery's dying, the old Fourier number here, transforms it into the new Fourier coefficients with this factor. And so now we have to start substituting in these shift operators and simplify, and you end up that a given point relaxation damping factor for a given mode wave number k gives you all of this. So this is effectively something that is going to be less than 1. We subtract 1 for it, so this is generally going to be negative. So we take 1 plus something times a negative value, and we end up with a reduced value. If k is large, let's substitute that. So we were saying, well, let me make sure I'm not doing it here. I won't. OK. So if k is, for example, n divided by 2, so that is the fastest wave number we would have, h is 1 over n. The 2's cancel. This ends up being pi. Cosine of pi is -1. The biggest value this can have is -2. And this looks like something that could potentially damp that highest wave number mode if we choose a lambda that is correctly aligned to that wave number. Similarly, if k is very small, this thing is going to look like 2 pi kh, so 2 pi h. Superfine problems, h is going to 0, and we're going to end up with something that is effectively close to 1, and this is only mildly negative, so we're not going to damp it very much. And in fact, what you do is you make a substitution of this beta parameter, which ranges from 0 to pi. And here are some plots that you can see. What does this look like as a damping operator for, I'm worried I'm going a little fast here, but I think I'm okay. As a damping operator for one pass of point Jacobi for all the wave numbers you might have in a given problem. So, for example, I was just talking about that a choice of 1/4 for the highest wave number, that would be a plus minus pattern, kills it right there, 0. Which is good, because if I have this kind of content, in many cases, I don't know if you talked about smooth representations versus high frequency content, but in most numerical simulations, those plus minus modes aren't physical, right? We don't have things in real life that are plus minus noise as much as they're distributed spectrum noise. So getting rid of those generally will improve the fidelity of your answer. If you pick a different choice, like lambda is equal 1/8 to try to, you'll see that the damping overall of that error is not great. If you choose a different thing, like lambda is equal to 1/2, that would be the maximum time step you could take without this thing blowing up, trying to get more out of it. You're now damping all the way up to this middle of the spectrum, but in fact, for the higher frequencies, you haven't done anything. You've just flipped their sign here with a -1. And so this would be an ineffective scheme for doing getting out high frequency noise, but it'd be a pretty good scheme for these middle wave numbers and things lower. It's the most damping you're going to get. So you might take one sweep of one sweep of another, try to iterate around and get all of that error down, but you're not going to win, because in the end, this here is not damping the error at all. The smoothest numbers you have, wave numbers you have, and the finer resolution it's going to be, the more you have to iterate on it to get that error to go away. And this is an important case, because if you said, well, suppose I just want to get rid of these somewhat non-physical high frequency wave numbers, because they're not really in my numerical analysis. It's not what I'm converging to. They're just grid noise, more or less. Well, you can choose a value exactly of 1/3, and that puts this damping parameter here and this damping value here at the opposite ends, so they both damp the waves. The highest frequency flip sign, but they do damp, and the lowest frequency in that range damps straight down. So that's actually, for the rest of the lecture, that's the value I'm choosing, because I'm trying to get rid of high frequency modes, and now I want to address these low frequency modes in a different way. So basically, we get the high frequency sweeps done quickly. And if you think of what a plus minus pattern or those high frequency patterns look like, you can see them locally. If I did a Fourier transform on just the local part versus the global part, you would end up with the same frequency content, because most of it's contained in the local oscillations that are varied quite a bit there. If you had a smooth mode, you need to see more of the wavelength, which means a bigger part of the problem, in order to actually capture that and know that that's what you're looking at. Kind of reminds me of the wise men and the elephant problem. Anyway, so as n increases, these smooth errors for j is equal to 1, if you just substitute that in there and simplify it, you actually see that for the Laplacian here, that's your damping factor. So some constant times your grid spacing h². We can't change lambda any more than that. That's the maximum value of lambda before the iterative scheme would blow up. So this is the best we can do for that kind of a wave number. And so if we can't get these to converge very fast, think about what this is, right? This is an 1/n² amount of reduction in the error for a given iteration. That means we need to do n² of them to get a fixed amount of error reduction. But we also have, in 1D, n number of points. In 3D, it would be n³. So basically, we have to do something like, in 3D, the size of your domain, which is routinely 10,000 or 100,000, to the 5th in order to get a fixed level of error. That's just not feasible, right? So we need to be smarter than that. But basically, if we could somehow say that there's a coarse version of the problem that represents these smooth modes well, why don't we just try to solve that problem instead? It's a lot cheaper. We get these smooth modes much faster, right? Because again, that h² just doubled or quadrupled or multiplied by 8 in order to, and we can get much more damping there. And then somehow we need to merge the answers together. And that's effectively the story of multigrid, is how can you take advantage of point relaxation to get rid of high frequency components, coarsen the problem somehow so you get rid of low frequency components, and then do that in a way that iterates back and forth so that you can get it all. All right, how's the pace? Do you want me to speed up or slow down? Are we good? Okay, good, all right. So here's the multigrid algorithm. You have some approximation you're going to say, that's my guess, just from a couple of sweeps of point Jacobi. Get rid of the high frequency content. Then I calculate a residual, right? So this is how far off my right-hand side is from my current solution and the exact solution. And then I coarsen that residual. Basically say, all right, well, if it's got a lot of high frequency content or whatever, it shouldn't at this point, but I'm going to coarsen it to try to take a point relaxation sweep there and make more progress on the low frequency modes. And so when you put all of that into this correction equation, you now have 2H, so a twice as coarse grid. You have the residual that came from the finer level, and now you're going to do this point relaxation sweep. One important thing here, though, is that lambda is a function of 2H, no longer of H, because I can take bigger steps. And basically keep doing this. If this were the whole domain, after one coarsening, I only have 1 degree of freedom, right? So that's easily solved. That's a diagonal. And now the question is, how would I take these values and propagate them back up here? Well, you do this thing called interpolation. And when you interpolate something between mesh resolutions, you end up introducing content you didn't know was going to be there. So I'll show you what that specifically looks like. But once you've interpolated it back up, you do some point relaxation sweeps because, again, you're trying to kill the high frequency modes, you trust the coarse solution, and that's it. Now the thing is you have to do this recursively and ad nauseum, but at least you've written down a very simple algorithm now. And you can see just in 2D, we went from 9 degrees of freedom to 1 degree of freedom. All right, so we reduced it effectively by about a factor of 4. In 3D, it would be by about a factor of 8. And so you can very quickly turn it into a small problem that you can solve faster and more easily, and then try to get back your fine problem again. So here's what it looks like in code, and it's really short, which is nice. Once you've written your point relaxation algorithm here to apply the operator and relax it, you can do that as many times as you need to get rid of your high frequency content or mid frequency content or whatever your goals are for this, because this is just one kind of problem. Multigrid get applied, it's like a religion. It gets applied to so many different kinds of problems. And if you're interested in talking about some of those, you can ask questions or ask me afterwards. But then you take this residual, you coarsen it, you set, this is important, you set your coarse guess to 0, because if your residual is the difference from 0, right, because the residual, when it goes to 0, you have your answer. When you've coarsened it, you want to say, my initial guess on the coarse grid is going to be 0, because that's where I would like to be. And then when you take a couple of those point relaxation sweeps, it makes that correction fix the residual, and so you call it again. And when you come back, when you interpolate it, you're taking a correction and you're adding it to your existing solution on this level. So it looks like a V cycle, and each part of the V is relax, coarsen, go do it again on the next coarsest level. And when you're done with all the coarsest levels, you come back up and you interpolate your corrections back onto your solution. So it's not a lot of code, and each of these things is very easy to code up. You've effectively done most of them already. The question is, what do these interpolation and restriction operators look like? Because they really affect how quickly you converge overall. So and it depends on your discretization and your equations. If you have a variable coefficient equation, you might end up with different interpolation operators. If you have finite volume or a spectral element method or these things that all have different kind of mathematically optimal algorithms. And some of them actually will converge faster depending on how much information you put into them, but then it's that trade-off between coding effort, how fast the algorithm is, how fast the algorithm converges. So this is all where you start to get into a bit of voodoo about multigrid religion, and it becomes very problem dependent once you get away from these simple model problems. But to start with, there's this great reference called a Trottenberg multigrid, and it's a tome. It's quite hefty, but it's a great reference. You can look up everything from finite element methods to algebraic multigrid methods and other things. So I'd recommend you take a look at it if you're getting into multigrid to an extent. All right, so let's look at these average operators. So this concept of conservation of charge, that is, if I had let's say all of these summed up to 1, I would want to make sure, or all of these were constant and I summed them up, I'd want to make sure that I ended up with kind of the same thing on a fine grid as I would on a coarse grid. And so if you think of what would be an approximation between that value and that value for a residual, it's effectively piecewise linear interpolation or contributions from a bilinear interpolation in 2D. So that would be basically, if you summed all these up, they equal to 16, divide by 16, so I would have essentially the ability to preserve a constant on this domain or on some small part of the domain. For a second order accurate nodal point thing, we basically do a dimension split interpolation. Again, if you had 1 here, you would say, well, what's the value between the boundary and the center? Well, it would be a half, but if I'm doing a bilinear contribution from these 4 points, then that would be a quarter. But if I'm at that point, that's a value I trust already from a coarse grid, so I'll just keep it. So effectively, this is the interpolation, or sometimes it gets called prolongation operator. And so if you think about it, I had a bunch of constants, I coarsened it, I got the exact value back, I distribute it back out, and this would effectively preserve those hats or other shapes that would be able to go from coarse to fine grid and back, with small corrections for other things. So basically, once you've coarsened it down to a problem that's only this big, or even 8 by 8 or 16 by 16, you just brute force it. You solve it with a lot of point Jacobi relaxation, or you do a direct solver with a LU or something else, and very quickly you get an answer, and then you're able to propagate it back up. The primary issue at scale with these things is, suppose I had 1,000 processors, and I've reduced it down to a problem this big. How do I take a problem that big, which was generated, each of those points from a different processor and those from different processors? What you end up doing is, it's called collapsing or condensing. You take work from different processors and you move it onto a smaller set of processors and then a smaller set of processors. But I know you're not doing much parallel stuff in this course, but these things are tricky to implement at scale. And again, it's better to use a library or to at least work with existing code bases that scale. So basically, 3 levels in 3D leads to a reduction of 512 in the number of unknowns, which is a pretty nice reduction. 4 or 5 of those, we do 15 levels, 16 levels. You do get into some arithmetic issues where you get round-off errors propagating up and down. So it can be problematic at scale, but it's pretty good in general. All right, so let's look at a specific example in 1D. I like 1D because you can get a lot of things clarified. It is not indicative of the amount of work, but it's certainly useful. So here's a right-hand side. This is the F value, where it's just piecewise constant. And if you think of the Fourier transform of this, it's got a lot of high-frequency content because it's like a Gibbs function-like thing. And in fact, if we know what the solution is on a piecewise basis, which is just a parabola, right? It's quadratic is the second integral of a constant. And you've got this little kink right in here where the third derivative would change. Well, it doesn't exist, but basically where this jump happens on the second derivative. So that's the exact solution. Now what happens when we start applying multigrid to this? So let's look. So this is just going back to that point Jacobi only. If we took 128 point Jacobi, look what happened. It propagated the boundary errors in from that constant and 0 into the interior, but it didn't do much to fix the error. In fact, the error is pretty bad relative. It's like 0.9 left before, it's only made 10% of the progress. Suppose I take 8 times as many, well, it's made it halfway there. But by the time I've taken that n squared number, it's the magic number, I'm up to, you see the black line is hidden under the circles. So basically, that's my order n cubed amount of work to get to a decent level of error, just using point relaxation. Now this one's a little harder to see, but let's start from here. So if I coarsen this all the way down to its 1, 2, 3 points, and I do that piecewise linear interpolation all the way back up the hierarchy, that's what I get. It's a horrible answer, and the error is about a quarter, I think, at these points, right? But it's tracking. And if I did that only from 4 levels down, well, now I've got 1 digit, almost 2. Got my 2 digits with 3 levels down. You can barely discern them anymore. If I just solved it on the second coarser level or the first coarser level, I'm already doing better than the order n cubed work. So somehow there's this balance of solving the coarse problem versus point relaxation on the fine levels. And so that coarse solution there is a really important way of evaluating, did I solve the right problem on the coarse level? And did I represent it as best as possible on the finest level that I'm interpolating to? So let's look at that specifically. So this is the FFT of my final solution, right? Because it's a parabola represented in Fourier modes, has lots of frequency content going all the way down to the highest wave numbers. So if that's what I'm trying to get to, this is what happens if I just take that first course problem, solve it, and then interpolate it back up. It's a dead-on match for anything that's smooth in its wave numbers. And it's not a great match at the highest frequencies. And that's because we did a piecewise linear interpolation. We put it on the fine mesh. And if you think about what that has, it's got this plus minus zigzag mode that it introduces. And it doesn't track the exact solution correctly. So if we did that for 2 levels down and propagated it back up, now we're starting to really introduce a lot of errors. So we took too much of a shortcut, we got greedy. 2 levels down, and not only did we have that first level down error still in the solution, but now our guess is also messing up the mid-level errors. And as we saw, point Jacobi is horrible at fixing these. And you can see it's even propagating into the smooth parts of the error now too. So again, maybe we got a little greedy. If we did 3 levels down, now we're solving the entirely wrong problem, right? We don't have the right frequency content anymore. Point relaxation, even solving on the course this level didn't help. And getting back here or here, we can solve with point relaxation schemes, but this stuff is the problem where we get back into the it takes n cubed iterations to fix things correctly. So if we think, though, point Jacobi is actually really effective at all of these frequency ranges up here and can even be tuned to help out here, although it's not great still. So let's put it all together. So if we did a V cycle, which I'll explain, but it's that pseudocode we saw where it's relax, coarsen, relax, coarsen, relax, coarsen, and at the bottom, solve as best you can, and then interpolate, relax, interpolate, relax, interpolate, relax, all the way back up. That's just called a V cycle. It's doing great. It's still got a little high frequency content because of the damping parameter that I chose, but it's killed all of the error here. It's still matching the coarse or the smooth frequency numbers very well. And that's exactly what we want, right? Now the question is, how much less work is that than an order n cubed point Jacobi approach? Well, for one of those sweeps, it reduces the error each time, multigrid V cycle, by about 12x. And that's using only 2 point Jacobis, not 2 times n, but just 2 sweeps, and then 2 after the interpolation. The reason you do 2 before is if you think about removing all those degrees of freedom to coarsen the residual, what you're actually doing is I could have super high frequency content in there that would get aliased by the operator onto things on the coarse grid that I don't want to consider, I don't want to solve. If I solved for that aliased error, I would be introducing error into the problem instead of removing it. And the same thing with the interpolation. We saw that by interpolating up to a finer grid, we're introducing a high frequency content that doesn't help us necessarily. And if we then propagated that up another level, then we'd be interpolating high frequency error onto higher frequency meshes, and it would just deteriorate. So basically, take it all the way down to a 3 by 3 grid, or in this case, the 3-point grid, point Jacobi up and down, and a V cycle, and you get a factor of 12x reduction in the error every time you do this. And how much work was it? So for 1 point Jacobi on each level, we have 2 of those down, 2 of those up, so there are only 4 is the constant out in front of n there. The average interpolation operators are the same cost, right? Because they are effectively 1 sweep of the domain collapsing down onto a smaller number of variables. So all those add up to order n, where the constant's like 8 to 10, depending on how many of these you do. And then each coarser level is 1/2 the work in 1D. And again, in 2D, it would be even cheaper. That would be a quarter, that would be a 16th, that would be a 64th. And so basically, this is an order n algorithm. Even though the constant out front can be pretty big depending on how much work you do, but it's so much better than the n cubed of point Jacobi. Now, the caveat on all of this is this just like, you know, nothing works in theory, right? Everything has to work in practice. So this is a model problem. This is ideal convergence. This is why you start off with this. If you start throwing in things like discontinuous meshes or discontinuous jumps in your coefficients or boundary conditions that are changing in time. A lot of these things can really deteriorate as soon as you get to nonlinear problems. But this has become so pervasive that it gets used, for example, in solving aerodynamics problems for Boeing, right? I mean, this is real commercial code now at this point. So just to kind of go through the whole thing. So a coarse grid correction is good for its low frequency or its low wave number component, but it has a lot of high wave number component from the interpolation operator. We know that the coarsest point relaxation scheme does a really good job at things that look to it like high frequency, which is why we can use point Jacobi there and get away with that. That recursive algorithm only takes order n operations, where n is your number of degrees of freedom. In 1D it's n, or in 3D it would be n cubed. Doesn't matter, it's all in the same order. And it's very problem dependent though. You saw that there was a range of parameter tuning for point relaxation, and there's a lot of freedom with the interpolation and averaging operators. You can end up with either getting a 20x factor reduction in error or only 1.1. So this is one of those things where the magic and secret sauce kind of come into the problem too. Discontinuous coefficients are one particular problem. So imagine you were solving a heat equation where one part of the domain was metal and the other part was ceramic, right? So the metal acts like heat can go through it like water, and the ceramic is just not conducting heat very well. So if you coarsen that, the edge where those two things meet are bouncing around from each coarse grid depending on what grid points you're intersecting and how far away from the grid points are. So you can actually be introducing a lot of error on the coarse grids from that representation that's no longer nicely resolved. So that would be an example. Sorry, didn't realize I was clicking a button. And then one of the things that we talked about a little bit was the interpolation operator should represent the smooth components well. And so what that means is if my discretization error is good for a smooth component, then I would expect interpolating it to the same order of accuracy would give me a solution that's pretty close in terms of discretization error. So what that means effectively is that it's basically it's saying that I could do a better job of interpolating to get a good answer as long as I have some way of correcting that error. Like, for example, a near null space means that it's going to damp out the high frequency components of the error very quickly. In other situations, the near null space is stuff that would basically not be represented on a coarse grid, which could be these jumps or other things. So basically there's a lot of theory around this. There are many, many different flavors of it, and there are a lot of unfriendly examples too. That Trottenberg book that I mentioned before is a really good reference. So this is something from our group. This is a 3D combustor basically in this kind of a channel. Or is this the plasma chute? I can't remember which one this is. I think it might be the combustor. But basically these are adaptive mesh boxes, and each of these boxes is a, let's say, 16 cubed structured grid domain. And so you're solving all of these nested boxes on this large domain, this entire tube. You've got to solve the whole thing with these geometry cutouts and other things on it. And this is the multigrid convergence. So for a given iteration, this is how much it reduces the residual. So from 10 to the 14th up here all the way down to 10 to the 0, which is about as much as you're going to get with a double precision round off sensitive algorithm. And so I believe the convergence deteriorates a little bit as you add AMR levels. If you've got just a coarse level, we have that ideal convergence that I showed you before. But as you start to add these extra boxes and the interpolation algorithms between the coarse and fine grids and the complex geometry kicking in and out, you get a little bit of deterioration in the rate. Generally, if you see an algorithm kind of settle into that kind of a flat slope, there is a mode in there that your multigrid hierarchy is not directly addressing, or it's the one that's kind of least damped by your multigrid residual. Oftentimes I will take something like that and I will run those problems through an eigenvalue solver to be able to see, okay, what is the primary nature of that mode and how is it not getting damped? And usually I can take that and turn it back into a more steeply descending thing by just asking, how do I need to change my parameters or my interpolants in order to try to get that better? But that's kind of how complex this gets. And you know, this domain is probably a billion unknowns, which, you know, again, with an order n to the 5th algorithm would be impossible. So let's see what else now. So I don't think you've had any discussion of finite volume methods, have you? None at all. Okay. So finite volume methods are quirky. Instead of a node-based concept, you end up with the thought that this is a cell average. And if any of you have done any kind of physics course, you know about conservation within a control volume. So for example, for the Poisson equation, you use the divergence theorem to turn this into a difference of gradients across all of these faces. Right? So the divergence of a gradient is your Laplacian. So instead, you do integrate this over a domain, which in this case is just a box, and you end up with this representation of a difference of that angle bracket there means to the average over the face. So when you've done that, you basically have a nice way of discretizing any domain. This is just a square rectangular domain, but it's something that basically respects the physical properties, which is that the heat goes as a gradient, and whatever was in there has to reduce by the exact amount that left. All right, so those kinds of control volume approaches can be really important for things like shocks. I've done one with solidification before, where the rate of solidification very much depended on whether you captured the amount of heat left over after the solidification, right? And so if you want to get things like dendritic propagation or other kinds of interesting effects, or get the shock speeds right, conservation can be a very important thing. So basically, you end up with this equivalent, this discrete equivalent of the divergence theorem, but expressed as a formula where you're differencing or calculating averages on faces and across volumes. So for our group up at Lawrence Berkeley, this is our kind of bread and butter, because those physical representations are really important for things. So let's talk about this form of the Laplacian then. So if those gradients look like a difference that's an average across a face, and I started with these cell averages to the left and the right of the face, then a simple gradient would be a difference of those two. And this is accurate to second order in H. And what you end up with is something that is exactly the same discretization that we had in the nodal point. But this is representing a gradient on a face instead of just a Laplacian at the center of your stencil. So even though you ended up with the same discretization at second order accuracy, if you went to fourth order, if you did different boundary conditions, if you had a variable coefficient problem where maybe this gradient was multiplied by some conductivity or other thing, then you would end up with different discretizations. But at its root, those things are the same. But the important thing here is that because we have this physical concept of conservation and fluxes, that it behaves very different with multigrid. Multigrid now you need to think about, did I conserve charge as I coarsened? Did I, when I'm calculating a boundary flux, am I calculating it in a way that's consistent with the PDE at this coarse representation? So all those things play together. So let's look at that a little more specifically. So for example, if we were going to calculate the distance between this cell center of our finite volume and a boundary where we were trying to emphasize or enforce a homogeneous Dirichlet boundary condition, we could do something simple, which is basically say, you know, delta x is, so delta phi goes from 0 to the value in that cell, and then delta x is basically half a grid cell width. So I'm going to approximate my gradient with this. It looks like a gradient from 0, but only over half the distance, so it's twice as big. And so that would be one way that you'd see a different operator for finite volume than finite difference. And then if you think about what it is to coarsen these 4 cells, or these 8 cells, it's basically taking them and merging 4 cells at a time, but we're merging their volumes. So if each of them had a different value, it doesn't matter. We're just going to add them all together, and that would be effectively the value at the coarse level. And because we're dealing with average quantities, we would just divide it by the coarse volume, and we're back to where we were. So you can see that this is different than the nodal values, where we would have just dropped some of these. Instead, we end up with cell-centered values. So, this is how it looks a little different. So again, just a simple summation for averaging down to a coarser level. And again, this is a charge conservation, conservation of mass, momentum, energy, however you want to look at it. And then for going up, there's an interesting thing you can get away with, which is that as you go from these coarse values back to these fine values, you can just copy them into the same cell. Incredibly cheap. It's not even piecewise linear consistent. So you could ask, why can we get away with that? Well, again, we can go back to Fourier analysis and other things to analyze it, but it comes back to your intuition, which is that, you know, if we take these coarse values and we copy them in those dashed lines onto the finer mesh, all we're doing is adding this 2 delta x mode, and we'd be back to what would otherwise be that same piecewise linear solution that we had there. That 2 delta x mode is very easy to get rid of with point Jacobi, right? So even though it's barely consistent, it's only first order accurate, in combination with this ability to pick out those Fourier modes that we don't want on the fine mesh, it's a very cheap and effective way of propagating it back up. Now, if this were a more complicated domain or were higher order finite difference operators, you cannot always get away with this, but again, this is some of the magic and secret sauce of multigrid. And you know, instead of doing these piecewise quadratic interpolants that have to be then borrowed from other grids in order to do a 3-point interpolant, communications needed, et cetera, we just got rid of all of that by doing a piecewise constant. All right, so you can really save a lot of effort depending on what you're going for. And so in the end, this is actually Phil's code. This is your visualizer, and this is the result of your FFT. So this is all stuff you have in your hands already to be able to analyze the convergence of multigrid for this simple product of signs in Poisson problem. So this is the initial error, right? Just that one mode, which is k is equal to 1, right? So it's a plus minus sinusoid filling up the domain. And you can see that's, you know, the fast Fourier transform. This is 32. So let me see if I did the math right here. Yeah, I think that's right. So the maximum value with divided by n would give me something around that. And this is on a log scale, you can see, with, and this is just the absolute value of the coefficients for the Fourier transform. So if I did one multigrid V-cycle for this problem, instead of being up here at this value, it knocked them all down by basically an order of 10, but also shifted some of the Fourier modes. So because this is symmetric in this way, we're not going to get every Fourier mode filled in, but these are the ones that still exist after 1. And notice that it took, you know, effectively the smooth mode down a little bit and introduced some other errors at the higher frequency modes in compensation for that, but nonetheless they're all damped. And then after 3 multigrid cycles, they're all down by, you know, basically a factor of 300. So it works very well in 2D as well, and in this case the amount of work is even less on the coarse grids. It's very appealing in 3D. You know, we got away with a lot in terms of the interpolation that's piecewise constant, or the averaging, which is basically this direct summation. And the only thing I will caution you, because you have to think about finite volumes differently than these node-based finite differences, is first of all, you know, this has now 16 points in the interior of the domain instead of 15 points in each direction, right? And then when you do your FFT, don't forget to shift it by that half a cell. If you don't do that, you'll see all kinds of crazy frequency content. And you're like, what? I thought I just had a simple representation of this, you know, wave number 1. But no, in fact, once you shift it, then pop, you know, all of that collapses down to that point. So if you do use FFTs for your finite volume schemes or anything that's a cell average or centered, then you have to do that little shift in the FFT, but it's very simple to do. So any questions at all about kind of implementation from a finite difference nodal value or a finite volume standpoint? Yeah.
So what other options besides point Jacobi are there, and are there any advantages to doing anything besides point Jacobi?
Yes. Again, I can recommend Trottenberg, or I think on one of the earlier slides I put in Briggs' multigrid tutorial. Point Jacobi with different damping factors, that's one option. There's something called successive over-relaxation, where you take super large time steps. And that usually is kind of a Gauss-Seidel, meaning you replace as you go. Point Jacobi calculates a residual and then replaces. And then there's also something called Gauss-Seidel with red-black ordering, where you skip every other cell and do that sweep to fill in the values. And the red-black ordering allows you to basically kill a 2 delta x mode in one pass, as well as damp the middle wave numbers pretty well. And in fact, if your stencil has width, so a radius 1, so it's a 3-point stencil, that's a good choice. For higher order operators or ones with diagonal elements, you can do multicoloring. So you can do 4-color or 8-color in 3D. to be able to like hit each of those points separately and then damp them. So those are for those problems. And those are just the easy choices where you really at different flavors of point relaxation. For other problems, I've actually done small matrix solves on that part of the domain. So for example, if I've got problematic boundary conditions and I want to propagate it away from the boundary, you can do a small LU on that matrix. Again, it's cheap until n gets huge, right? You can also do line relaxation, which is basically you do a tridiagonal solve in the direction of one of the grid lines. And those are really good at damping the error in that way, but it decouples the problem. So you can end up having two different, it can introduce low frequency components that are in both directions because you've tried to decouple them. And honestly, at the end of the day, you could do any or all of those at different levels of the hierarchy to different degrees. So basically, explicit point Jacobi, some kind of local solve, tridiagonal or pentadiagonal solves, and one line relaxation. Those are the big choices usually. Any other questions? Yeah.
Like what kind of interpolation schemes are available? Like you mentioned linear and bilinear, but other.
Yeah, they all just look like what you'd do for standard polynomial interpolation. One of them that I use a lot is piecewise quadratic because it's relatively cheap. Gets rid of that 2 delta x mode on interpolation and is generally a little closer to the solution when you've got a constant in that domain. For high order accuracy methods, there's this thing called a full multigrid cycle. So instead of going all the way down and back up, imagine you just start by coarsening the solution all the way down to the bottom and say, I just want to know what coarse problem I should be solving, and then start propagating it back up one level at a time as I fix it. That's called a full multigrid cycle. And for those, the theoretical convergence rates are much better if at the very last step you do the highest order interpolation that you need to most accurately represent your operator. So it might be a 4th or a 6th order accurate interpolation. And in those cases, you can show that your convergence doesn't deteriorate with the number of levels of depth or with the operator. So there are a lot of different things. There are also, again, if you have a jump in the problem so that you know that there's a physical kink, you can do interpolants that are one-sided, all right, where you say, don't grab a value from the side where the coefficients or other values are different. Just work with a one-sided interpolant because we know it'll be more accurate than trying to interpolate through a kink, for example. So those are all options too. Good, thank you for the questions. Okay, so I think this is getting close to the end. Here's another real-world example with these. This is actually from a vortex method, I believe, where these are spots of high and low vorticity. And those are, again, those blocks of 3D boxes that are 16 or so cubed. So again, billions of degrees of freedom. And here's just textbook multigrid convergence. Now, because this is a, it's called vorticity stream function, but this particular problem is a Poisson problem, so you're going to get textbook convergence. But it's a 4th order finite volume method. So again, you have to be concerned about those higher order interpolants and what does your relaxation scheme look like, and am I getting all the high frequency content and things like that. Oh, and I forgot to mention this. This is really important. So a lot of what I showed you was the frequency content of the error in the solution, right? But if you remember, all of that was predicated on us knowing what the final solution should be. In the real world, all you know is how bad your residual is, right? So I have a guess, I take the Laplacian of it, it gives me a right-hand side that is different than the one I want, right? So typically, these are the residuals. Now again, if there's a scaling between the two of them, you're able to look at the residual reduction, but I could actually I could give you a starting value and a scheme that would make the residual go up, even though the solution itself was getting better. And then it will settle into its long-term behavior of this kind of nice convergence once you've gotten rid of those initial bad eigenmodes. So don't be discouraged if you see a couple of kinks on the way up to get your problem solved. What you want is that long, quick march versus iteration, and as you double the size of your problem, the iteration count should change only minusculely. Like log n is usually what the mathematics will tell you. All right, so let me see, what else? Heat equation. So caveat, I think the slides that we posted, Max, need to get updated because Phil and I were going back on the relaxation parameters and other things for these, but I'll quickly go through it. So to go all the way back, point Jacobi was like advancing the heat equation in order to get a solution to the steady state heat equation, which would be the Poisson equation. Suppose you want to solve the heat equation now, right? You've got to go back and modify everything you were doing. So again, heat equation, starting at time 0, going out to some fixed time. You put some right-hand side that can now be a function of time in there too. So you could have a reaction that starts happening when it gets to a certain temperature and really cranks out a lot of heat and then shuts down, for example. So that could be a source term. And if you look at the explicit forward Euler discretization for this, you've got this factor now which says I have a delta t that has to be less than some constant times h squared, otherwise this will blow up. And again, it's that fastest wave number problem. The discrete problem, as you refine it, the time steps get worse and worse and worse, because look at that. I mean, h squared, and in 3D, you're taking smaller and smaller time steps. So you've got basically this huge factor multiplying how big a time step you can take for this. So this is why we want to solve the problem, try to get rid of that delta t dependency and kind of figure out a decent way to do the implicit solve with multigrid. So with backward Euler, that would be an implicit scheme. What you end up doing is solving something that looks like the Poisson problem. I don't think that is that right? Yes, great. Okay, so now you're trying to solve an operator, which is the basically implicit heat equation operator here. So I minus delta t times the Laplacian. I always help keep the sign straight in my head because Laplacian in Fourier space will give you a minus k squared for its action on a Fourier mode. Therefore, this is a minus and a positive number. Therefore, I can work with it as a friendly operator in this kind of an equation. So basically, now we're trying to solve this equation where this is some right-hand side to evolve the heat equation, and this is the implicit operator that I want it to get to. And in general, if you put some coefficient mu out in front of the Laplacian, so for example, if this were a heat conduction problem, that would be the conductivity, for example. Or actually, it's the diffusivity divided by the heat capacity, so it looks like a coefficient of diffusion is what it's called. And generally, mu is going to be greater than 0, meaning you always have positive diffusion of heat. And so now we need to solve this. So again, we put it in this point relaxation form. Watch out for the signs on these, so let's double check it. So this will always be positive because of the minus k squared argument I just made. If this is positive, then I'm going to be reducing phi anytime that this is bigger than f. So this has the right sign conventions on it. And we go back to that residual correction form where our correction delta is our difference between where we are now and where we want to be with the final solution. And you end up with this very nice simple form again where our operator is now this heat equation operator, I minus mu Laplacian. And we're looking at ways of reducing this. So the first thing I do is I say, all right, well, I already solved this problem once. What can I leverage from solving it again here? So here's what we would modify for a heat equation with the Laplacian. Here's that I component, right, with my relaxation parameter sitting out in front of the I. And then here's that one that we got from the old iteration value. And so this is now my damping. So let's analyze this. So if mu is large, which means that it's more like Poisson than it is like an identity, if mu is large, then all these other terms don't matter, and the only thing that's left that matters is this guy. And so then it starts looking like our wave number iteration. And for mu is small, this guy starts going away, and it looks more like identity minus whatever my relaxation parameter is. So if mu is 0, then I'm just solving phi is equal to f. I can make lambda 1, and I get there in one iteration, right? I just solve the identity, divide by the diagonal, and I'm done. So this converges much more differently than Poisson does. And don't forget that here we've simplified it by saying that diffusion coefficient is constant, but in the real world, it's variable. It could vary for a lot of different reasons. It could be a function of time and space. It could be a function of the solution and be nonlinear. So So it's good to be able to kind of know these different regimes in the Fourier mode, but the reality is you're going to end up with different wave numbers converging at different rates here. And then finally, if you kind of go through the same steps and you say, if we had that plus minus checkerboard mode, so that n/2 wave, and we substituted that into this equation, this becomes our -2, and we get the ideal damping relaxation parameter of this guy here, 4 mu over h squared plus 1 in the denominator. So let's think about what happens with this. So as h goes to 0, this becomes a very large number, right? And so that becomes a very small number, and it becomes more like Poisson. That makes sense. As we refine the Poisson problem, we get beat over the head with it a lot. But if mu is much less than h squared over 4, so basically canceling this and making it less than 1, then this relaxation parameter becomes closer and closer to 1. And you can kind of see that in this final point relaxation update scheme here that results from using that relaxation parameter. So if mu goes to 0, we basically are replacing we're making the new value of our point iterate whatever we choose for lambda, and it basically, if mu goes to 0, this whole thing goes to 0, and the correction is instantly fixed. So the low wave numbers can be fixed instantly if it's more so more like the identity equation than the Poisson equation. On the other hand, if mu is very, very large, this doesn't matter, and this basically ends up being a factor of 1/2. And now it looks back like we were doing for the Poisson equation, where it's a weighted average of neighbors, and we only get a certain damping factor depending on what is stable from the Poisson equation. So basically, it's the same kind of analysis. You can see exactly what wave number lambda you want to choose, and you can have different parts of the domain depending on the nature of your problem. Different parts of your domain could be converging at different rates for the heat equation. Now, I didn't include all of the kind of iteration matrices and other things for the heat equation, but if you want to talk about it more, I think that's my last slide. Yeah, that is. If you want to talk about it any more, I'd be more than happy to go over details or whiteboard some things. But I think that's it. That's all I have. So any other questions? Yes, sorry.
Is there any hope on using this in any sort of hyperbolic problems?
Did you cover that with pair in 228? Probably not, right? No. So the classic one, can I use the whiteboard? So I'll try to write big so you can see it. Oh, thank you. Classic advection problem, let's say. So in 1D, let's say we have some solution that looks like this, and it's an advection equation with some positive velocity u, and at some future time, it's just going to look like that, right? Where, let's say this distance is something u times delta t, right? So that's a hyperbolic problem, purely specified. So what would happen if I coarsened this? Let's pick a couple of points here. Let's say that these are the values on the coarse grid. Here are the ones that I want to have. Look how completely different those are, right? So if I did a coarse propagator and I got it down and I moved it across, depending on where it sits relative to these grid lines, I may or may not be at the right solution. So for purely hyperbolic problems, multigrid is not a great answer. Usually, it's a good bet when you have advection diffusion, or when you have, for example, like a viscous term in a Navier-Stokes equations, because as you refine that viscous term, it gets more and more stiff, and you need something more and more like a diffusion solver for it. If you're just doing pure hyperbolic problems, and you're trying to apply multigrid to it, it might be a good preconditioner to get a first guess, and then you could do some kind of Newton or point relaxation scheme on the finest grid. But in general, you avoid purely hyperbolic problems with multigrid. The only exceptions are ones that you can kind of recast in a elliptic system. So if you think of like a wave equation, that is a Poisson operator with a time integrator. So you can end up recasting that as a elliptic solve, but that's more like kind of a Green's function method if you guys studied Green's functions. And so for those you can use it, but for most of the others it doesn't do a very good job. Your best bet there is to do something that's kind of a characteristic based or maybe a more Lagrangian approach, things like that. Okay. Any other questions? Okay. All right. Well, I guess we start a little early. I'm sorry, end a little early. Again, my email's up here if you have other questions about multigrid, or if you want to encourage me to keep teaching, let me know. Okay? All right. Thanks a lot for your time.